So we have exam 4, then we have an exam 5 coming up, and then our final exam. So here is our review day for exam 4. It's days 17 through 18C. And here's an example, just trying to break things down into the different topics, the different calculations that you did. And one of the very first things is finding the pH of strong acid solutions, like 0.23 molar hydroiodic acid. How would you do that, Miranda? How would you get the pH of something like that? Yeah, just the negative log of 0.23. So that's not right. Hopefully there'll be a question like that, but I doubt bless you, there'll be too many. Right? Okay, Erica.
Yes.
Then we jumped into the pH of weak acid solutions. The 0.23 molar HCN. How would you do that? You have to make an ice table, right? So, okay, now ice table's right, but what ice tables always need a reaction. What reaction would you write? The Ka reaction, right? And you have to be given the Ka. I don't have those memorized, but you have to write the Ka reaction and do ice. Good. Okay. Do you want to see what that looks like? Okay. Usually all right. What we have been doing is doing this, which will work. And then do ice on it. That'll work. Just recognize HA as HCN is all, right? But it might look easier to follow if you actually wrote it out that way, right? And then put the 0.23 there in dashes. So this is a concentration table. This isn't like a mole table like we were doing later around day 18. This is a concentration table. So when you get your X, that actually is the concentration of H. Okay. Nyla, how about what's the technical? Well, Nyla, did you want me to continue with this, or do you see what to do? Okay, so as our get for X, yeah. Okay. So, Pedro, what is the technical difference between 0.23 molar HCN and 0.23? What are you supposed to say for F? Pedro, what are you supposed to say for F? For formal or formality? Formal or formality. Okay. So Adrian, what's the technical difference between 0.23 molar HCN and 0.23 formal HCN? Anybody know? All of its forms. F is all of its forms. Exactly. And the M means, hey, no, that form is 0.23 molar. Right. So 0.23 FHCN, that really means 0.23 molar equals what plus what? CN minus concentration plus HCN concentration. All of its forms. Yeah, good. Okay. So we spent some time, Pablo, talking about formality, and that was a general question. How about this one? The degree of dissociation of a weak acid.
That's the nonce divided by the formal.
It's what?
That's the nonce divided by the formal.
Yeah. He's right. Now, what was the little symbol? Because I was thinking of the little symbols. Remember, what is the alpha? But he's exactly right. I like how he said it, too. It's the XN ice divided by the formal concentration. And we gave it a little symbol, like you said, alpha.
And the X is a concentration. It's not the mole table that we.
No, we're mole table is really only for buffers.
Okay.
Because our Henderson-Hasselbalch we changed it. Well, I changed it. Moles of base over moles of conjugate acid. Okay, it makes life a little bit easier. Okay. Then the book kind of moved into, so we did some dissociation of weak acids and just kind of remember what Pablo said there. Dissociation of water. Jeff, what's the equation? What's the reaction when they talk about dissociation of water? Yeah, Kw, but what's the reaction?
When water actually breaks up.
To what? Yeah. Water breaks up and H plus. And I need to have a water over here, right? Right? That's our dissociation reaction. It happens naturally. The degree pretty much depends on, oh, there's a good question. Casey, the degree to which that chemical equation happens. What I mean when I say degree, I'm meaning I can actually get more product or less product. That's the degree. Can I change the degree to which that reaction occurs or progresses? Or is it just fixed? Like that Kw, concentration of products over reactants, and you get that number. You can change it. How? You're right. Okay, I could add, I see what you're saying. You could add some HCl or something like that. But that doesn't, that's just Le Chatelier's principle. It's a good point you brought up. Let's say I add some HCl. 250 milliliters of 0.1 molar. I have the same equilibrium going on. I have Kw still. Kw is 1 times 10 to the negative 14 is products over reactants. I didn't change the degree. I need to change what? So it's the T. It is a T. Temperature, right? Equilibrium constants. The only way to mess with them is really temperature. Unless you have a gas, then I guess you'd mess with pressure maybe. But okay. Here's our first type of question when we start getting into this dissociation of water stuff. Adriana, we have 1.23 molar KOH. Okay. Please name every ion in this solution, regardless of its concentration. K plus. Oh, I should probably write these down. Okay. K plus. OH minus. H plus. Everybody agree? Should the H plus be listed? Yeah, because of the dissociation of water. Yeah. Okay. Then describe the source of each ion, the source each ion in the solution came from. Okay, Miriam, where's this stuff coming from that Adriana named off? Miriam. The H and the OH, most certainly, that's one of, they're coming from dissociation of water. One of those, okay, let's list this out. She says dissociation of water for this, dissociation of water for this. Is there any disagreement? OH also comes from the KOH, good. And then the K comes from the KOH. So I don't know if you remember doing this kind of thing, but the point of it was to find something that only came from the dissociation of water. And that's the H plus in this case. And for example, they might have, if you remember doing the question, it was worded something like, what is the percent of hydroxide from the, in 1.23 molar KOH, what is the percent of hydroxide that is from the dissociation of water? So you have to find the hydrogen ion concentration, and then, because that's your answer, right? Because the amount of hydrogen ion that's from the dissociation of water is the same as the amount of hydroxide from the dissociation of water. So that's how we did it. We found the species that wasn't from the KOH or from what the solution was. Okay. Yeah. We probably ended up with a quadratic formula. Yeah. So you might want to review that a little bit. Maybe we can dig up a question when we're all done with this. I didn't dig one of those up. John, what is the concentration range where a systematic, remember that full systematic treatment, where a systematic treatment would have to be used for this system? In other words, what's the pH? If the question was what's the pH, what would you just do, John? Take the negative log, and then you get POH, so then you subtract from 14. So that would work. So he's right. So Kimberly, this question B is really, where is the concentration range of that KOH? Where you have to do a full systematic treatment. There's this worrisome concentration range. Okay, 10 to the negative 6. There it is. Someone's got a good memory. Or you found it. That's the worrisome range. Full systematic treatment. If it would say, I don't know, 1 times 10 to the negative 6 molar KOH, what's the pH? Full systematic treatment. Okay.
That's what the last test was on, the 5-step program?
Yeah.
Okay.
Yeah. But we had some of those in here too again. You have to just kind of have to go back to that region. Okay. Here's another one. Jamesa. 1.23 molar sodium fluoride. Name every ion in this solution. Na plus, F minus. Is that it? No. H plus, she says. OH minus. HF. Yeah, you always name the acid unless it's always try it. You just can't name strong acids because you can't form them. So you always throw an H on there. Yeah, HF. So, okay. And is that it? Yeah.
I have a question.
Yep.
What ions, did they have to have charges? So an HF?
Oh, I should say
everything? Okay.
everything besides water.
Okay.
Yeah. That's a good point. That's a trick question. HF shouldn't be listed. Yeah. Everything. Okay. And the source. Where's this stuff coming from? A little more practice, Kathleen. Where's the Na coming from? Yeah. In fact, we even know what its concentration is, right? It's coming from the sodium fluoride. How about the, you Randy, how about the F minus? Where's its source? From the same. Yeah, it's coming from here. Except, is it 1.23 molar? No. But it's coming from there. The H plus cat, where is this one coming from? The dissociation of water. Right. Okay. How about Amanda? Where is this coming from? The dissociation of water. Now it's also in a Kb reaction, but that's not its source, right? And the HF, Miranda. Where is this guy's source? Where's he coming from? Yeah, it's kind of a hard one, isn't it? I didn't notice that. I was just going to answer 8. I was just going to say this, but then you look at it, there's no H in there. So it has to come from, that's kind of complicated one, isn't it? Yeah. Okay, so that doesn't work so cleanly as I thought it would. Okay. Then we got, nah, maybe that's why. That's why. Well, it is me. I just wrote the... I'm just trying to get you to look at solutions, and it's kind of the guts of the full systematic treatment idea. Okay. Erica.
Yes.
You're the only one who ever says that. Why use a buffer in the first place? That's good. It's a good word. To regulate the pH. Control it. Yeah. That's good. Okay. So I got to pick on someone who has a book. And Nyla has a book. So, yeah. Oh, we don't need it yet. Sorry, I don't need that yet. I thought I was on this question. I'm not way down there yet. So Nyla, out of all the buffers listed in the table, how is a buffer chosen? Like for Erica's application there of controlling the pH. How do you pick a buffer? There's a gazillion of them. Yeah. As close to the pH as possible. Right. Okay. And pick a buffer that has a pKa closest to the pH that you want. Adrian, why is that? Why are buffers chosen in that way? Why? Anybody? The Henderson-Hasselbalch equation is a hint because the log would be mathematically the log of 1 is 0. Now what's the big deal? What's this log of 1 thing coming from? Remember what that Henderson-Hasselbalch was. pH equals pKa. Whoop. Well, you can change it to concentration, or it's really the same thing because volume cancels. But it was the moles of the conjugate base over the moles of the conjugate acid. So mathematically, you want log of 1. That means what, Pablo, if you have log of 1? All right. What's that? 0. Yeah, I know, but how do you get 1 out of this? Yeah, log of 1 is 0, but where's the 1 coming from? The moles of the base equals the moles of the conjugate acid. Right. They're equal amounts, equal populations. Okay. Because if you do add an acid, Jeff, somehow some acid gets into your system, into your buffer system, what would react with it? The conjugate base, right? So you don't know what's going to get into this buffer, so that's why you pick it right in the middle. Now, on the other hand, if you do know what's going to get into that buffer, oh, it's only going to be acid, well, then you probably wouldn't match pH equals pKa. You'd probably pick one that's going to have a lot more base in it, right? Because you could adjust your pH, or you could play around with it, I guess. Okay, but odds are usually buffers you don't know which way you're going to go, so don't worry about that. You pick the pH to match your pKa, and then it's the closest. Yeah, because like they said, this number is, I don't know, 18. This number's 18. 18 over 18 is 1. Log of 1 is 0. That whole thing's 0. So pH equals pKa. Right? Okay. So Casey, it's your first day on the job. A $25 an hour job at DPT. Okay, I want a benzoic acid buffer, and I want it now, and I want it at pH 4. What are you going to do? You're fired, Miranda. You hear what she said? Go make it yourself. That won't get you very far. Yeah. Okay. Doesn't get you off the hook, Casey. How do you do this? Yeah, find the moles first of the benzoic acid. Oh, there's no molarity. We need a molarity here, right? Of 0.29 molar benzoic acid. Okay, so she said find the moles. So now we can. Before we couldn't. So moles, molarity is moles over liters. So multiply the 0.25 times the 0.29 molar. Is everyone following? And get the moles. You got to get it into grams. Now, how do you get it into grams? Molar mass. Now, if you're really good at organic, which I am not, I don't know what the hell the formula is of benzoic acid. I can guess a benzene ring with an OH, but I could very well be wrong. How do you know these things? The table. These tables, they're all in there, right? That AP11 is where it starts. I'm going to provide you a big, thick thing or something. I'm not even sure where it is. But I'm not going to make it easy. I'm going to provide a bunch of buffers. So you got to pick stuff out, and it's just like a whole big table. Okay? So you're going to have to look at that structure and figure out what the molar mass is. Okay, so let's say you get the molar mass. We should probably practice that, though. What is benzoic acid? Is it this? You guys laughed at me last time I did this. That's better. Is that benzoic acid? That's phenol. Oh, it's a carbonyl. C double bond OOH. So they're going to do this, right? It's a coup. Okay. No. That's cheating. Right? Okay. How many carbons in that thing? Okay. Everybody agrees? 7. How many H's in that thing? 6. You should be counting 6, right? Because there's one H every spot, right? Because they're conjugated. So if you attach something to that spot, that H is gone, right? So there should be 6 H's and 2 O's. Everyone follow that? Yeah. That's important. Okay. Then you get the molar mass, add it all up, convert the moles to grams. We got it. Put it on the balance. Okay. We are really, really close, but that's not a complete answer, Adriana. Yeah, what do you need the grams for, Adriana? Then you're going to do what with the grams? Find the little bottle.
Oh, you're going to put, okay, you're going to fill it up with at least half. You're going to put it in a flask and fill it up with at least half water.
Yeah, okay. Okay, put a bunch of water in there, but not over 250. Yeah.
Then you'll add base and adjust it until the pH is.
Yeah. And what if you add base and it goes,
Oh,
or acid? What if you add acid and it goes to 2?
yeah, add base.
Base, and it goes up to 8. Then you add some acid. So you see why it's a big deal not to dump it up all the way to 250 right away. Otherwise, you're going to go over the mark, and you're only going to get paid $15 an hour instead of 25.
So you can add like 50% water, like.
Just a lot of water,
Okay.
because if you
No, like.
pure water is somewhat a little bit acidic. So if you dump in 100 milliliters of water, you could change. You went through all that work to get the pH right on 4.0, and then to have it go to 4.1 or 3.8, that would really bite. So you want to have a lot of water in there, right? I don't know. Like she said, over half, 200. I don't care. Just not 250. Okay. And that's how you make your buffer. Just keep bouncing around until you finally get the pH to be 4. Keep adding acid and base. Because all you're doing when you add acid and base, Miriam, is what? What's happening in this Henderson-Hasselbalch equation when you're at that last step that Adriana was talking about? Okay. So that moles of base number is getting, if you're adding acid, the moles of conjugate base number is getting, it's reacting, so it's getting smaller, and it's forming the conjugate acid, so that number is getting bigger. So you're changing that ratio, you're changing that log number, whatever it is, you add it to the pKa, you have new pH. So that's what you're messing with. You're just messing with that population. Okay. John, what is buffer capacity? We didn't talk about this too much. This is kind of just dependent on the reading, I guess. Buffer capacity. Now, Erica said the purpose of a buffer is what? Regulate the pH. Okay, so I don't know. Pretty much everything is buffered, right? This stuff is probably buffered. When the pH equals to pKa, you're right in the middle of the buffer region, right? Kind of think, this is how I imagine it. There's two words to describe this. If this is pH, that's my buffer region. And right in the very middle is where the pH equals the pKa. So that is my pH equals pKa mark. Okay, so you can go so far below the pKa, so far above the pKa, buffer region. That's not buffer capacity. If you go outside the buffer region, it's no longer buffering, right? But what's buffer capacity? The maximum, okay, you're getting there. The maximum amount of, because you're close. The moles of the conjugate base, the moles of the conjugate acid. There's only so much of it, right? You keep adding acid, like HCl or phosphoric acid. Who knows what's getting in there to make that thing more acidic? That conjugate base is doing its best to react with it and keep the pH relatively constant. But sooner or later, you're going to run out of conjugate base. And then your buffer capacity is gone, right? So to me, buffer capacity is this dude right here, right? that concentration of that stuff.
So the maximum.
Well, that's how I look at it as, right? Because the more concentrated that buffer is, the larger its buffer capacity. How about its buffer region? Doesn't matter. Doesn't matter because they didn't mess with the pKa. The larger the concentration, the better the buffer capacity. Right. Okay. Because the more moles of conjugate acid, the more moles of conjugate base you'd have to buffer acidic and basic species in the solution.
So then that answers the second question.
Oh, yeah. More concentrated buffer solutions have a greater. Okay, now one thing that's not covered is if that, let's say the pKa was 8.2, whatever buffer that is. What in general is this pH? And what in general is that pH? If that pKa is 8.2, where's my buffer region? It's pretty much the same for every single buffer. Doesn't matter what you pick. How do you figure it out? 7.2 and 9.2. Amanda's exactly right. It's plus or minus 1. Okay. 7.2 and 9.2. Good. That's the buffer region idea. So you're in the buffer region as long as it's plus or minus 1, like 7.2 to 9.2. So that's what they're trying to say. They're trying to say that, okay, this buffer is good enough to buffer something if you want to be between 7.2 and 9.2. And it's best at 8.2, but you can still use it in between 7.2 and 9.2. It's just that I think it gets worse and worse and worse on each extreme. But it's still usable, is what they're trying to say. It's still usable. You can still use it. So if you don't have a buffer that actually matches your pKa, fine, go by the buffer region. It's not as good, but it'll work. It's functional. Okay, now who am I giving my book to here? Okay. Kimberly, 8P12. Oh, we don't have to give them all. Just give, well, I guess I really might as well give them all, right? Hopefully you're on. You're going to give me the names of all the buffers that exist as A- when put in water. AP12. Now she's going to be, well, let's see if she does first, then we'll ask.
So the ones that don't have the H, ones that,
So
the H plus, so aspartic acid.
do you hear Big Bad John or Cat? The ones that have a charge, because you have to remove it.
So
Aspartic acid,
aziridine,
aziridine, benzolamine, butylamine. That's it. Just that page. All right. Anything that had a plus charge.
So basically,
On that page, I guess. How about this question? Let's give it to Jamesa. Would dissolved cyclohexylamine react with NaOH or HCl? So you off the shelf, you grab the bottle that says cyclohexylamine. Which one would it? Where is cyclohexylamine? Okay, here it is. Okay, so would it? Okay. She looked in the table. She says it has an H+. It has this big thing. So that means it corresponds to A-. this guy is a conjugate base. So that good. So it'll react with the HCl. Oh, sorry, the wrong question. This one. It'll react with the HCl. All right. All right. E corresponds to A minus. And then this is pretty much what the quiz was.
Can you go
Right.
over that? Well, the quiz that we had today, are we going to get it returned tomorrow?
Yeah, you can probably get. I should have it done during lab. Yeah.
Yeah.
But what you're going to do is write. Just remember, don't write Ka or Kb reactions. Write the actual reaction that's happening and make a mole table. So the actual reaction that's happening is A minus plus H plus makes HA.
As we can say, like, we shouldn't be it gave us like a KA and a KSP. So the quiz today, it wasn't like they didn't give us a KA.
I don't know what the quiz was. I don't remember it.
Yeah, because it's like all the homework and then they got this. I don't know
Well, there's no silver there. How can you? You don't even need the KSP.
So like I didn't really know how to do it.
I have a question. Can you just check these calculations? I think I did them right. So you do to find the molarity.
Okay, which lab? This is the one that we
We're
just.
doing acid. The one that we're doing.
This is one you're going to turn in
Yeah.
tomorrow. Okay, so you first we have to show a
Molarity.
calculation for molarity for HCl,
So did I?
and then I just have to remember
No, you're fine,
myself.
you're fine, you're fine.
Let me shut this off.
So you want like the calculation of molarity and weight percentage shown,
Everything,
right?
everything.
Well, no, like it actually typed out.